All right, so we are going to be talking about Module 12, the gas phase. So last module we talked all about solutions, and we talked a little bit about liquids, solids, and gases. Now this module we're going to focus just on gases. We're going to talk about what happens to them in their physical state, and we're going to talk about changes in their environment and how that affects the gas. And we're going to talk specifically about things like temperature, pressure that's associated with gas, volume, and things like that. So those are the main things we're going to talk about. First, we're going to start by talking about what is pressure. We're going to define it and talk about it a little bit. And then we're going to talk about the 5 gas laws. There's 5 gas laws that you need to know pretty well, and all the equations with it. So hang with me as we break down each law. There's going to be some equations that you need to memorize. Some of them you will just use enough that you'll know, because you'll be using them almost in every problem. So you'll memorize it, but you'll memorize it because you're using it. Others you won't need to memorize. Okay? So let's get started. What is the definition of pressure? So in order to understand the gas phase, you really need to know the concept of pressure. Pressure is simply just the force per unit area exerted on an object. Okay? So however big your area is, whatever your unit is, whether it's feet or inches or centimeters, it's the amount of force in that area. Okay? So we would say it like this: pressure equals force per unit area. Remember, capital A that you learn in algebra is area. Okay? So this is the technical term for pressure. Now, we're not really gonna go through that whole lot now. That's gonna be more physics related. So once you take physics, you're gonna be dealing a lot more with this type of stuff. But we just want you to have an idea of what pressure really means, okay? Now, when it comes to pressure, that's going to be your capital P, that signifies pressure. You're going to have 5 different units in this module that deal with pressure, okay? So sometimes they'll have a problem with one unit, sometimes they'll have one with another, sometimes you need to convert it to a different unit depending on what you're doing. So let's just go ahead and list them, okay? The first unit of pressure is going to be the Pascal, okay? And it's going to be abbreviated like that, okay? The second one that we're going to be dealing with is the kilopascal, okay? So this unit, we actually named this unit after a French mathematician, scientist, philosopher. He came up, he did a lot of things for chemistry and for physics. So in honor of him, we named one of the units a Pascal after him. So one thing to remember as we're talking about pressure is the gas exerts pressure on any object that it comes into contact with. So if you think about it, we've got gas all around us in our atmosphere. That's what our atmosphere is made up of, right? So depending on what the gas is, it's going to exert a certain amount of pressure up against anything it touches. Okay, so remember, think back, I think it was like module 4 or 3 or something like that when we were talking about gases before and molecules. Remember, when molecules and atoms become gases, they start moving around, right? The reason why they become a gas from a liquid is they start getting a lot more energy, and the more energy they have, the more they move around, right? Well, what happens? Well, as they move around, they're starting to bump into things around them, right? And the repeated bumping up against things is what causes that pressure, okay? So keep in your mind as we're talking about pressure this module, that the higher the energy, the higher the temperature, means the more it's going to be bumping around into things. So that's where we get the pressure from, okay? So the third unit we're going to be talking about is the ATM, which is an abbreviation for atmospheres, okay? So we would say that a gas exerts 1 atmosphere of pressure, okay? Let's see. Let me erase this really quick. Our next unit we're going to talk about is going to be the torr, okay? That's your fourth unit. Actually, this one's going to go, technically we're going to lump this one, the Pascal and the kilopascal. Okay, here I'll just bump all these up. We're going to talk about torr. Okay, so this is another unit of pressure, and keep in mind in physics we're going to be talking, you're going to be using these a lot more, so you're going to become a lot more familiar with them than we're going to be using them now. Another one is called millimeters of mercury. So if you look at this, that's the abbreviation for millimeters, and this is the elemental sign for mercury, so millimeters of mercury. Is that the last one? I believe so. So maybe we are breaking it down. I was wrong. We'll just put this as the fifth one. For the most part, we're going to be going back and forth between, I would say, maybe these three, but mostly atmospheres and torr. Those are going to be our main two that we're going through, okay? So, let me put up, it's already up here. So, these are our conversion units, okay? So, right here in the green, I put it up here for us to use. So, 1 atmosphere is going to be the same as 101.3 kilopascals, okay? These two are a lot easier. 1 atmosphere is also the same thing as 760 torr and 760 millimeters of mercury, okay? So we'll use those a little bit in this module as we're going back and forth, but you won't have to worry about it too much. All right, so let me go ahead and erase that. So the first thing we're going to talk about is we're going to talk about Boyle. And grab my other magnet. Okay, so this is the first thing we're going to talk about. The first law. We got 5 laws. Okay. So, so now that you've learned the definition of pressure and the different units that are associated, we're going to talk about the couple different laws. Okay. Robert Boyle, he was an Irish scientist, and he determined that as long as the temperature stays the same of a gas, that the product of the gas's volume and pressure is the same, okay? So these are the equations that come out of this. So this is pressure and volume and pressure and volume. So what he said was the product, so these are being multiplied, pressure times volume, as long as the temperature stays the same, it's going to be constant. So what that really means in real life is if I have a gas, and that's what the little 1 signifies, I have a pressure and a volume being multiplied. Well, it's going to be equal to the pressure and volume of the second one. So what that means is this is how you should be thinking when you hear this. It tells us that when the volume of a gas goes up, okay, so if I have, gas in here, and I have more, you can see the volume went up of gas in here. When the volume goes up, pressure is going to decrease. So that should make sense to us, right? Because the less space, the less volume of a gas you have, the less area the gas is going to have, and it's going to be boing, 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 boing. It's going to be bouncing off around the walls, right? So the smaller space, the more it's going to hit around, causing more pressure. So if you give it more volume, it's not going to hit the sides as much. Therefore, you're going to have less pressure, okay? So they're inversely related. So in the same way, if you have the volume, instead of it increasing, let's say the volume decreased, so you can see there's less volume here, what's going to happen to the pressure? You should be able to see it now. We got less space for the gas to be in, which equals it bouncing around even more, so there's going to be a higher pressure, okay? So when the volume of gas goes down, the pressure is going to go up. And you can see this on page 385. This is what they're showing here. And the pressure that you see, if you look at the top, there's like this little gray weight, okay? The size of it's changing, okay? So as it gets thicker, that's signifying that there's more pressure. Okay, there's more pressure on there. And you can see the volume changing as well. Now remember, this is implying that the temperature stays the same, okay? Because we know from last module that when the temperature of a gas of the surroundings changes, it's going to change the energy. Remember, when we add heat, it adds energy. So this is when the temperature stays the same, okay? All right, so I'm going to go ahead and take this one down. That's Boyle's law, okay? Now, let's put up Charles' law here, okay? Oh, and really quick before we hop forward, Robert Boyle, who's the Boyle's law is named after, he is considered by many to be the father of modern chemistry. So he's a pretty important guy. Okay, so let's talk about Charles's law, okay? So this one's very similar to the last one, to Boyle's law, except now we're going to be talking about volume and temperature. So this one is assuming that pressure remains constant, okay? So the amount of weight that you're going to see on the figure on 387, that pressure is going to stay the same, and we're going to see volume and temperature changing now, okay? So what Charles' law says is the volume divided by the temperature is going to stay constant, okay? So that's how we get this, the first gas, and this is the change to the second gas. What that means in practical terms is it tells us that when the temperature of a gas increases, volume must increase. Well, that makes sense, right? So if I have my beaker and I've got my gas in here, and all of a sudden I put flames underneath it, what's going to happen to that gas? It's adding energy, and when you add energy, you're going to increase the amount of times it hits on the side, which means you're adding more pressure. So what's going to happen? In order for the pressure to stay the same, what's going to happen to that container? It's going to need more volume. So if the volume can't change, then the pressure is going to increase. But let's say the volume can change, that this can actually move up. So if the temperature goes up, the volume's going to increase so that it can disperse that pressure so that the pressure stays the same, okay? So likewise, if you have a gas and instead of this, you put it in ice cubes, okay? These are my ice cubes. It's not great. So when you cool it down, what's going to happen then? Okay? You're actually decreasing the pressure because you're decreasing the energy. So what's going to happen to that volume? In order for pressure to stay the same, that line can't be the same anymore. It's going to go down now because these aren't hitting the sides as much. There's not as much pressure. So to compensate for that, your volume's going to go down, okay? So these are proportion. So these change proportionally. So if the temperature goes up, the volume goes up. If the temperature goes down, the volume goes down. So remember, this law, Charles' law, is really important because it leads to the Kelvin temperature scale. So remember last module we talked about Kelvin, okay, and what that means. And in this module, we're going to be talking about absolute zero, okay? So remember, volume can never, think about it. If you have a volume of something, it can never reach zero because if it reaches zero, you don't have any of it anymore. Okay, so a volume can never reach all the way to zero. It can only get close, okay? So think about that. If the volume decreases but can't get to zero, what's going to happen to the temp? It's also going to decrease based off Charles' law, but it's never going to get as like ultimate cold because if it gets totally to zero, you won't have any volume left. You won't have it. So this is what we're talking about absolute zero. Okay, so if you look at the graph at the bottom of page 387, you can see they kept cooling these gases down. And you would think naturally that it would go all the way down to zero, but it can't because then the volume wouldn't be there anymore. You wouldn't have anything left. So the coldest it's going to get is 0 Kelvin, okay, almost 0 Kelvin, or negative 273.15, which should be familiar because that's the number that we use to convert from Celsius to Kelvin, okay? All right, we're going to stop there and go to the next video.